Hello everyone, my name is Hongyan and I'm a PhD student from NUS. And I'm very excited to be here to present our work, Efficient Privacy Auditing in Federated Learning. And this is a joint work with Brandon and Anindya and Reza Shokri from my supervisor. In this work, our goal is to provide an on-the-fly auditing algorithm for parties so that they can continuously monitor their privacy risk during the federated learning process. In federated learning, parties are repeatedly sharing their local models with the server, but the sensitive information in parties' local dataset can be encoded in these local models. So the information about their training dataset can be leaked to the server through the shared local models. And this information can also be leaked to other parties through the global model. Now, to measure the information leakage in machine learning, the de facto standard is to use membership inference tag. The goal of the adversary here is to infer whether a target data point is used for training or not, given some access to the model. The information leakage can be quantified by the success rate of the adversary. Now, in the federated learning setting, parties share their local model in each round. So it means that the adversary can infer the information from multiple model snapshots. And this means that the adversary can observe the entire training dynamic. Using the membership inference attack framework, parties can monitor their privacy risk by running the attack algorithm locally, inferring the membership based on all model snapshots. Prior membership inference tag algorithm designed in this federated learning setting explored this training dynamics by training inference models. Specifically, the adversary extracts all the information from each model snapshot and then train a very deep, complicated models on the concatenation of all the signals from all the model snapshots. Those signals can already be computationally expensive to get in practice. For example, the per sample gradient is very costly to compute. Give one example here. If we are training a ResNet on CIFAR10, computing the per sample gradient could take 380 times longer than local training. So if parties want to extract the per sample gradient in each round, the federated learning process could take 46 GPU days compared to 3 GPU hours before. So in addition, training the inference model on the concatenation of signals would further increase its cost. So this approach is also particularly not feasible for parties with limited resource in practice. On the other hand, if we look at the membership inference tag designed for centralized setting, strong algorithms also require training additional models. The goal here is to train a set of models to simulate the model behavior when the target data point is in or not in the training dataset. However, this method can also be costly. And in addition, since those methods are designed for attacking a single model, when we apply them into the federated learning setting, they overlook the information encoded in the entire training dynamic, which may lead to an underestimation of privacy risk. Now the problem is, how can parties effectively audit the privacy risk without training any additional models? Our solution is motivated by how the performance of the model changes over different rounds. First, when we examine the model performance in any specific rounds, we can see that the results for members and non-members are overlapped with each other, and it's very hard to distinguish them based on the signal. For example, here is a prediction confidence for the members and non-members at around 60. There is a large overlap between two groups. And this significant overlap can be observed in every round. Here is the average prediction confidence score and their standard deviation for two groups. And we can see that this overlap between two groups can be observed in every round. Now, when we examine the performance dynamic over time, we notice that this prediction confidence score increases more rapidly for the members compared to non-members. So the intuition here is that each model update should impact the model performance on two groups differently. So their performance should change at different speed. So to capture this distinction, we introduce the slope signal, which measures the rate of change in model performance. Specifically, for each data point, we can compute this slope signal by fitting a linear function to its performance dynamic. And the slope of the fitted function serves as a signal of interest. The advantage of using this slope signal is its efficiency. Model performance can be evaluated based on confidence score or the loss or the losses. Those information are typically computed during the federated learning process in order to keep track of the training. And the slope signal itself is just a weighted sum of models' performance across each round. So it's very quick to compute. As a result, parties can audit the privacy risk in real time. Given the slope signal, the party or the auditor can compare the slope with a threshold tau. Then if the slope is higher than this threshold, the point is predicted as a member, otherwise it is predicted as a non-member. Now for each value tau, the party can measure the true positive rate and false positive rate. The party can iterate over all possible tau to get the whole ROC curve here. Following prior works, we use the true positive rate at a low false positive rate to measure the privacy risk. And this metric reflects the attack accuracy when allowing small number of errors. Our auditing algorithm can be seamlessly integrated as a plug-in module to any federated learning pipeline. During each round of training, parties can update the global model using their local dataset. And then before sharing it with the server, the party can run our auditing algorithm locally to monitor the privacy risk. The example here showing on the right illustrates what a privacy risk report may look like in federated learning process. And since our auditing algorithm can be calculated almost instantly, so parties can take immediate action based on the auditing results to further enhance their privacy. For example, they may apply differentially private mechanism. Now let me show you some empirical results. Here I'm showing the results when we train a ResNet on CFR10 using Fed average within 4 parties. And we compare our algorithm with baseline attacks in terms of the efficiency, which is quantified by the GPU time required in each round, and the effectiveness, which is measured by the true positive rate at 1% false positive rate. The results are calculated based on the whole training process. We can see that in terms of the performance, our auditing algorithm stands out as the most effective and efficient option. Our algorithm achieved 12.9 true positive rate in just 1.2 seconds. In contrast, other algorithms are either ineffective or inefficient. For example, the membership inference tag algorithm, which requires computing per sample gradient, could take 860 seconds per round, while the TPR is still 2.8%. In comparison, local training only takes 2.3 seconds, so the cost for those methods is pretty large. Other efficient membership inference tags are not effective. And moreover, if we look at the strong membership inference tag designed in centralized setting, here I'm showing you the results for Lyra attack. Even with additional power to train 16 reference models, the performance does not achieve the same level as ours. The reason is that those methods are designed for a single model. And this gap highlights the importance of leveraging the whole training dynamic for auditing privacy risk in federated learning. Due to the efficiency of our auditing algorithm, now we can study how different factors could influence the privacy risk in federated learning. And this analysis is prohibitively very expensive using prior strong membership inference tag algorithm. Here, I'm showing you how the privacy risk evolved over time, along with the model performance. We can see that after round 50, even though the model performance remained almost stable, the privacy risk continued to increase. However, if you use the efficient membership inference tech baselines, those algorithms fail to capture the increasing pattern in this context. We also study how the data heterogeneity affects the privacy risk. Here, I present the average privacy risk across 20 parties, and along with their standard deviation. If we look at the non-IID setting on the left, the standard deviation is much larger than the IID setting on the right. This indicates that parties in federated learning are experiencing different levels of risks, particularly in this non-IID setting. This phenomenon has been overlooked in the literature due to the lack of efficient auditing tools. And furthermore, we can observe that as the data heterogeneity increases, the average privacy risk decreases, and this trend cannot be observed using baseline attacks. To conclude the talk, in this work, we propose an efficient auditing algorithm which enables parties to continuously quantify the privacy risk during the federated learning. The core of our design is this slope signal. It leverages the information encoded throughout the training dynamic. We show that our auditing algorithm is effective and efficient. We also provide a comprehensive analysis about privacy risk in federated learning across different settings. And if you are interested, please check our paper for more details. Yeah, thank you.